Hello everybody, my name is Eric, and today I'm going to be showing you guys how to simulate OBJ files such as this F1 wing in OpenFOAM, and then also how to see the results. Here's a little snapshot of what you can see, and what I'll teach you guys how to do in this video is this front wing. You can see everything from the vortices on the edge, and then also the high pressure on the top and the low pressure on the bottom, shown in blue. I'll show you how to do this, and it will even run in about 20 minutes on your computer. So, quite impressive. This is part 2. So, in part 1 we talked about how to install OpenFOAM and the basics of Linux. So, I'm going to assume that you either know that or have watched part 2. So, without further ado, we'll get right into the video. I'm going to be doing everything in the command line. So, I hope you're somewhat comfortable with that. To recap, basically what we did is, in last video, we went to CD foam tutorials, and we took the incompressible case of the simple foam example of the motorbike, and we copy that into our downloads folder, or documents folder. So CD home, your name, then documents, and then we made a simulations file, so CD simulations, and then we can see our motorbike file. So if you didn't watch the first part, install OpenFOAM and copy that, and you'll be caught up. So then our next thing is to go grab our OBJ file, and yep, we can grab this from this Reddit thread, reddit.com Formula 1. This will be linked in the description below. And it's quite an old car. It's the Williams 3B, so I think it was from 2021. Yeah, 2 years ago, so adds up. You can grab it from this download link, and this download link is a Dropbox link. And it has these things, so you can download it. It'll show up in your downloads. Okay, in here there's 3 things. 3D models, screenshot, and textures. These are all other things that I added. In these 3D models, you just have all these OBJ files. I also added this folder, don't worry about it. Some of them are useful, some of them aren't. Like, let's say this Williams.obj or Williams.racing.obj is just purely cosmetic, so no sense in adding those. There are some good ones though. Rear wing, nose with the number on it, that's the actual nose. Front wing is also good, and then, as I mentioned in the last video, you have the turning vanes and the barge boards. These are all good ones to simulate, but we're just going to do the front wing, but you can do whatever you want. So, what we'll do is we'll find the front wing. It's in alphabetical order, so it shouldn't be too hard. Front wing, great. Front wing, we'll copy that, and then we will go to our simulation, motorbike, constant, geometry, and paste it in there. Great, so now it's there. What we'll also do is, now that we're back on the command line, we'll also go to the system folder and then look into the snappyHexMeshDict. And then we can see that it's looking for a file name motorbike.obj. What I'm going to do is I'm going to copy this. Yep, I'm going to copy this. I'm going to go out, and I'm going to go to the constant geometry folder. And here we have that front wing. What I'm actually going to do is I'm going to rename this. So you do that with move front wing and then paste the new name. And then it should rename it. So now it's motorbike. So now we don't have to go through and change it. This is not really like great practice, I think, but it is easier because now we don't need to change anything basically. So that's our OBJ file added. Maybe one thing. Let's say you only want to simulate half of it. Then there's a somewhat easy way to do that. So constant geometry motorbike.obj. So here's the front wing. It should look like a front wing. If you only want to simulate half of it, I think the best way to do that is with this clip command. So with this clip, then it will make a slice, and if I click apply, then it'll only do one part of it. So what you can do is do Z normal, and then it will only give you part of it. I think it's a bit better to have the right half, so just do -1, click somewhere so it like updates the value, and then apply. Okay, then you have this. My computer can't handle the whole thing, so I like how it looks with the whole thing, so I'll just let it. Oops. Better just delete the clip, actually. Yes, so what we need to do here is we need to figure out the bounding box while we're here. So you don't need to have the exact bounding box, but you need to think, what is the simulation of error we're going to simulate around this? So the best way I've come up to do this is with the ruler. And we're going to also find something out here. So let's first orient ourselves. The X direction is the way that the air flows over the car. The Z direction is the width of the car, and the Y direction is the height of the car. So if you ever played Minecraft, it kind of works. So let's first see how wide the car is. So right now this line is from 0 to 0, so not super helpful. But let's try like 1 meter to -1 meter. This is something what I would think an F1 car would be like. And then you can see, let's also change these to zeros for clarity. So now it's just measuring 1 meter to 1 meter. And here you can see, oh man, this is now saying like the car is like 20 meters wide, because this is like a 1/10. And indeed, that's kind of true. What happened here is that the leaked files were in centimeters, and now this is in meters, I believe. So you need to scale it down. It's like getting confused about the units. So the way to do that is you go to the OBJ file, filters, yeah, filters alphabetical, and then it's transform. Oops, bottom right, transform. And then scale, simply just do 0.1, 0.1, 0.1. And then click apply. Great. To recenter yourself on the data, you can do one of these two buttons. They do the same in this case. Okay, great. And now you see that the wing is like a bit over 2 meters wide. It's still a bit too small, but okay. So now we're in the right order of magnitude, and this is correct indeed. Okay, so now we see that the front wing is shifted forwards. If you're wondering why this is, I believe it's because Formula 1 will simulate from the front axle as the 0 point. So everything in front of the front axle is negative, and everything behind the front axle is positive. So that's why it's negative. So let's first find the front point of our simulation, and I already happen to know a good value, so we're going to set our x value equal to -1.5. And this is probably pretty good. Like, this is still a little bit extra space. You could probably be even more aggressive if you wanted. Like 1.25 would probably work. Yeah, but for me, I don't mind having a little bit of extra space. We'll do 1.3. You can do whatever you want though. And of course, if you have a different part, then this number will change. Okay, so we'll go with 1.3. As for our width, let's now put this a bit closer. So we'll just do -1, so it's directly underneath. And then we can put our camera in this direction. So you can see that we're barely wide enough, but this is probably a bit too tight. So we will change the width to 1.5, I guess. Yeah, so now we're definitely more than fine. In fact, this is almost too big. Yeah, so we'll decrease the width by a bit. So we'll go 1.2, -1.2. Yeah, this should be fine. So let's write this down real quick. I'll make a notepad file, I suppose. I normally write it on paper, but it's not great for you guys. So in our x direction, we will have, so negative 1.3 is our minimum, and we still need to determine our maximum actually. 0 might be enough actually, because it's kind of also nice to see what happens after the wing. Yeah, 0 seems like a nice number. So there. Our y values we still need to determine, and our z values we said from negative 1.2 to positive 1.2. Oops. Perfect. And our y values we need this way. Let's again, so the y minimum value will be 0 because we want to use that as the floor, similar to how they did it in the motorcycle case. That's great. And as for the positive value, we just sort of, let's find out. Let's try 0.5. 0.5. Yeah, should work. It's a little bit high. Maybe go 0.4. This is all just to make it a bit, like the tighter you make it, the more cells, the less cells you'll have to deal with. Yeah, let's go 0.5. I like to have the extra space, but it's personal preference. You'll see maybe how much results you have. I'm going to save this file in our simulations, and then I'll just call it domain. Perfect. One thing is that we need to save our transform. And the way to do this is file. I think you need to select this file, save data. Yeah. And then what we'll do is we'll just call it motorbike.obj and overwrite it. Yes. That was regarding time steps, and it doesn't really matter. And maybe we just make sure that it's all correct. So we'll just open up paraView again. I get nervous if I did it right. Constant geometry, motorbike obj, open, and then a ruler. Yeah, already it's looking better, but we'll just go on z negative 1.2 to positive 1.2. Yep, and then it's the right width, but this has a, yeah, good enough. Right, we said 1.2. Yep. So we'll close it out, and then it's like, so in principle we could try running it right now, but it won't work. And what we're going to do for this approach is we're just going to go through the all run file and think about what we need to fix. So we'll do nano / all run. Okay, so we'll have to run all these manually. You could also remove these and then do it. Surface features. So I think that one will actually still work. We can double check, and then after that will be blockMesh. So that's what we need to think about. So let's just change to the system folder, and then we'll look into the surface features Dict. Here we see that all it's doing is motorbike.obj, and we kept the name the same, so no need to change it. But if you did change the name, then you should change it here. So nothing in that folder changed. However, in the blockMesh Dict, things will change. We need to update these values with the ones we just had. So let's do that now. I don't really like how they did this. So what I'm going to do is I'm going to introduce each variable. So I'm going to do xmin, xmax, ymin, ymax, zmin, zmax, and then just put the value there. So let's open the text document. We can put them alongside each other. xmin negative 1.3, ymax 0, ymin 0, ymax 0.5, zmin negative 1.2, zmax 1.2, and then semicolon after each one, I believe. Great. And then we have to throw these in the vertices. So yeah, just simply like go here, and then you see that for their simulation it was between 5 and 15 on x. So this should be xmin, and I'm just going to go down to all of them. Xmax. And the same thing for y and z. So just simply replace this with ymin, and etc. So I will do this and catch up with you guys when I'm done. Okay, so I'm back. I did it. You can see that there's also a little pattern here. So it goes 4 min, 4 max on Z, then it goes 2 min, 2 max, 2 min, 2 max on Y, and then for X it's 1 min, and then max max, min min, max max, min. So you can double check yourself. One thing I did forget is that all these should be indexed with $signs, or prefixed with $signs. And then you're done. So this works the same. They should have done this in my opinion, but okay. Then these are all the other patches. But we actually don't, okay, I'm not smart enough to see it. I'm sure someone is. But should we move the ground patch? So what we're gonna do simply is we will just go up a folder. We'll ls, then we'll blockMesh. So then we make our patch, we make our simulation domain. Great. And then we will do paraFOAM so we can view our mesh. Click apply. Here's our mesh, and then we'll file open constant geometry motorbike. So then it's there. So you can see at least we don't see our motorbike. That's because it's inside the domain. So that's good. What we're going to do to double check is we will remove some stuff to see if we're in the right, if everything's right. So let's just deselect everything, I guess. Inlet. Is the inlet patch correct? Yes, it is. Okay, by default the outlet patch is probably also correct then. Yep. And then let's do the lower wall. So this should be the ground. This isn't correct. So right now it's simulating it like this, so that the air is here, the ground is here. So we need to change it. So what the best thing to do is to go to Firefox. You can go to this link with the mesh generation, and then you can see this is how the OpenFOAM geometry is defined. And basically what we're saying is that yeah, some of these need to be switched. You have to use this as a reference frame, so x1, x2, x3, that's x, y, z. We can open paraView next to it. Yeah, so what does this mean? Well, if we try to copy this in our paraView, then we see that we have the same axes lined up. So we have x in this direction, y pointing backwards, and z going up. And then they have that here, x, y, z going up. So we've oriented our case, and then we see that our ground patch is on the bottom. So then that means our ground patch is face 0, 1, 2, 3. That's the numbers. So we'll do that right now. Ground is 0, 1, 2, 3. Great. Back to paraView. Then we want the ground to be the one that's facing towards us right now. So we want it to be 0, 4, 5, 1. The order does matter, whether it's 0, 4, 5, 1 or 0, 1, 5, 4, but we'll just copy it in the blockMeshDict. Okay. That's all we need in paraView right now. So we can close it out, open the command line again, ls cd system, and then do nano blockMeshDict, and then we will see the inlet. Sorry, the lower wall right now is 0321. So let's change that on our notepad. 0321. So the numbers were right, but the order was wrong, which is fine. And then we want it to be 0451. So we need to find a patch that has the same number of those. So this one, 1540, the same numbers as this one. So 1540. And now it's just simply a matter of, just changing it. We should actually also then do the upper wall too. So upper wall is 4567, and we want it to be across from the lower wall, which is going to be the other front and back panel. So then it should be 3762. So now we just have to go through and change all these. So just go up here, change these to the old patch numbers. So Control O to write out, enter, Control X. So let's go back up, and we'll block mesh again. I think you need to do force. Guess you don't need a force. You also see a nice little diagram. I've never seen that before. That's nice of the OpenFOAM people. Okay, so we'll do paraFOAM again to load our geometry. Thank you for telling me paraFOAM is ready. Click apply. File, open, constant geometry, motorbike. Okay, apply it, and then we will hide all the mesh parts. Now let's test inlet. Yep, seems good. Outlet, good. And then the big one, the lower wall. Yeah, that's correct. Front and back. These are symmetry planes, so that's correct. Yep. They're symmetry planes though, so if you did only submit half of it, then this front and back should be right in the middle of the wing, and then it would say that it's symmetrical over the other side. An upper wall, sure, why not? Bing. Nice. So this is all correct. We did it. Yeah, so now let's look what's next in the all-run file that we can maybe change. So blockMesh should be fine. decomposeParDict will do that, and snappyHexMesh. So change to the system folder, and then nano decomposeParDict. So this is saying then how many cores are going to be on each place. So they're saying that we're going to do 6 cores, and they're going to be 3 in the X direction, 2 in the Y direction, and 1 in the Z direction. I'm going to change mine to 10, but you should do whatever yours is. So you can open up System Monitor to see if you haven't done that already. System Monitor you can also find in your apps. Here I can see I have 12 threads, 6 cores, so take the number of threads. I would not take the whole thing, but 2 or 1 less is fine. Yeah, so I'll do that, 10 cores. So 10, then these 3 numbers need to multiply to add up to, or multiply up to 10. So first we need to change it to like 5 and 2, and then the order here is important. So X, Y, Z. So if we think back to our thing, our length is this one, so it's 1.3, and then our Z is by far the widest. So we need to have our most cores on our Z. So we should put the most on our Z. We'll put 5 there. Our Y, we can probably get away with 1. And our X, we will do the 2. So now each one has like about 0.5 meters-ish. So each square should be about 0.5 by 0.5 meter. 0.5 by 0.5 by 0.5. So that's sort of the idea behind this. And then X, Y, Z. Perfect. Depending on how many cores you use, you might need to get creative on how you do this. but that's fine. So that was the decomposeParDict. You can also leave it if you want, but that's fine. No, you should definitely not leave it. You should at least change the XYZ to different numbers. That matches our case. And next is probably like the worst file here is this snappyHexMeshDict. Yeah. So I have to be honest, this is definitely like my weakest area because I never made my meshes in my courses. They were always given to me. Well, I never made meshes like this with snappyHexMesh. I did make meshes, but never with snappyHexMesh. So yeah, this is definitely my weakest area, and I think there's a lot to improve here. So if you guys have any advice, leave it in the comments, or also just play around with stuff. But it is somewhat time consuming, sadly, these steps. But I'll just show you something that works. Okay, refinement box. So you have to tell it what area to look in. This should probably just be your domain. So we will just open this up again. And here, this is a different format, of course. Why not? So that's the first thing we need to do, so we've at least specified where it is. I'm not going to go through all of these, but you could. Settings for the mesh. Max local cells. I will just leave it. Max global cells. I changed this to 5 million. That's fine. This minimum refinement cells. So this is just the max global cells is how many cells can exist in the domain. 5 million should be fine. Minimum refinement cells. So it will do iterations until every cell is figured out. But sometimes you get really stuck on the last few. So they tell when do we skip. I did 30, I think. It should be fine. Load unbalance. Yeah, should be fine. Hey guys, Eric from the future now. After this, I basically did not change anything else in this file, and then I tried to run it, and it took basically an hour. And then I made some changes, and it went much faster. So I'm going to show you now the changes between my original and my current file, and in this way it ran way faster. I could also include this whole story, but for the sake of the video I'm just going to cut it all out. So now we're going to jump to myself further forward, where we're going to see now the faster base case, which only takes about 10 minutes to decompose and 10 minutes to run. Thanks. So here I have my updated case. So I called it motorbike fast base case, and then here's the old system. End cells between levels. This can make quite a big difference. I changed it to 2. That helps for sure. Especially you keep down the number of things. I did level 5 refinement. This could maybe even go lower. And then what you should do is you should change. If you change this to 6, or if this is 6, it should be 5, 6. If it's 5, then it should be 4, 5. So we'll also change this down to 4, 5. I think a lot of everything else stayed the same. Oh, refinement box. This went down also 1 level. Refinement box region 3 went down a level. Inside point was fine. Let's see settings for the snapping. 3, 2.0. I changed this number of solve iterations down to 20 also. Shouldn't be too crucial, but maybe saves a bit. I think the only other thing that I changed was this layer addition. I changed to 40. Yeah. So I'll have this available in the description, or you can go through it yourself. But we'll just copy it from line 44 onwards. Control C, and we'll go back here and paste it. And this should give us a bit better. Yep. The only thing is, I think the name of the file is now wrong. Yeah, front wing scaled emesh should be motorbike. So make sure to change that to whatever you had. Motorbike.obj is still fine. It's only in there twice. So save that. Refinement regions, we can leave mode inside, so it's going to look either inside or outside the OBJ file. It seems to be backwards though. And you need an inside point. Don't ask me here, but you need a point that's outside the mesh. So what we'll do is we'll just take one that's by next to the corner, and or you can take anything just this basically on one edge. So take this. We'll say x is like negative 1.2999. You should never do the very edge because it can't be on a face. It should always be inside of a cell. So that's why they have these little extra bits. Y will do 0.4999. And Z, just do the center a bit to the left. So we'll write that out. And in principle that's done now, but it's okay also if we come back to it later. So this is just an initial guess, and this is how it always works: is you run it, you see the results, and then you see does it need help. And eventually you find a good case. Also, I know that there's some time left on the table that can make it run faster, but this will at least give us a working case right off the bat, and then we can probably easier have a working case and then try to speed it up rather than have a non-working case and try to make it work. Yes. So let's look at our all run file and continue down our checklist. Patch summary, that's just checking the patch. Potential foam, we don't do anything on. Simple foam, it's just running. So we're actually almost done. The one thing is we need to do is we need to look at the simple foam file. So this get application is just to make it more broad. But our simple foam, you can see it inside system. It's not really true, but you can look at the controlDict here. And here's our stuff. So application simple foam, that's where it's like it's getting the application from there, and then running this one. Start from start time 0, stop at end time 500. I have no idea why they did this. It's so silly, but why anyone would ever simulate for that long is insane. We'll try this. Maybe we see that it crashes and then we change it, but for now it'll be fine. So I changed the end time to 0.03, the delta t to this number, and the write interval to 100. So that means every 100 times it will save. So we'll get a save at 0.1, 0.2, 0.3, so we'll have 3 time steps. Just to prove that it will be a steady state. And then let's also comment these out. Oops, so this is not MATLAB. Let's do that with 2 slashes. Yeah, maybe we could also go into these files and fix them. Oops, I think I screwed something up. I did a tab. So you could also go into streamlines and fix this. So you would be, you know, changing the uniform line and that sort of stuff. Okay, so in principle now everything's done. So we'll basically just start running things. So we'll remake our blockMesh for the surety of it. If you forget what to do next, then you can just do all run. Okay, blockMesh, then we need to decompose the decompose, and it said copy 0 afterwards. So it's actually already done. So you can see now that there's a bunch of processor files. I already forgot what to do again. I think it's snappyHexMesh, and it was override. What's the But this can be done in parallel actually. So I just copy pasted it. So I looked it up. I'll leave it in the comments. But it is this mpirun. mpirun number of processes 12. We only want 10. So this is basically saying that we're going to allocate 10 to the snappyHexMesh. Going to run it in parallel and overwrite. However, if we run this, it won't work. This is because we want to use threads instead of processor cores. At least in my case I do. So then we need to use this command also instead. Control-C this. You can go up to access the last command and then throw it in there. And now it should work. So now we see that OpenFOAM at least started. You can see 10 processes, 9 slaves, and it started initializing stuff, and now I realized I forgot to do something. Basically, it couldn't find the motorbike.emesh file. That's because we didn't run the service features. So we'll just check the command in the all run file, but that's the service features, which I never ran. This doesn't take very long, so yeah, should be done. And now let's try again. Okay, and now it's going. So, yay. This is all saying things that doesn't really matter. It does matter, especially if you're trying to limit or reduce the amount of time it's spending. You could spend a lot of time reading through this log file and seeing where you're leaving time on the table. This process will probably take like 10-15 minutes. And okay, right now it's 8:30, so let's see how much of an improvement we have now. So this is much better now, only 7 minutes later. Let's check the mesh. So reconstruct paraMesh/constant. This should go much faster than last time, basically because there's less cells. Check mesh, CHECK mesh, and you can see it actually runs in some reasonable amount of time. Number of cells, 1.2 million. That's fine. Yeah, we don't really care about the rest. And we'll do paraFOAM to make sure our mesh is of an acceptable quality. This is like qualitative now. If you wanted to, you could reduce some more numbers and make it even lower, but that's not really strictly needed. Okay, so as we did before, mesh parts only want the motorbike part, which is equivalent to our wing, and you can see it's a pretty nice wing. If it's does some weird stuff while you're zooming in, don't worry about it. It just always does that. So you can see it's not perfect. This element here is a little bit choppy, but overall this took 20 times less, and for basically the same mesh quality, this is acceptable to me. You can probably even make it better. I don't know if there's some OpenFOAM wizards out here who can make it even better than they could, but yeah. And you can see even this element is extremely thin, but it's still quite acceptable. So yes, I think we'll leave it here. And now it's time to run it. So let's basically re-look at our all run file, our checklist basically. And then we see, okay, they want us to do patch summary, not strictly required, but we'll do it anyway. Okay, so let's run patch summary. And here you can see some basic stuff. Yeah, nothing too interesting. And looking back at our all run file, next thing is to run potentialFOAM in parallel, ideally. So here we have this. Then we'll get rid of the overwrite, and then we'll change this to potentialFOAM. I don't think I say spell potential, to be honest. Yep. I'm not very good at spelling. So we'll just select this, copy it, go up, paste it. Okay, so then it fails. I think I have a fix to this. I just have to make sure. I really don't know why this happens, but this online forum had the same thing. They managed to solve it by doing decompose and the snappyHexMesh in parallel, which we already did. Restruct paraMesh constant, which we already did. And then delete the 0 folder from the processor folders, and then do decompose again with forcing. So I actually figured out why it does this sometimes. Perhaps. I think it's because when I did the decompose, I did not do the copy 0. I think if you do the copy 0, you shouldn't have this problem, but if you do have this problem, you can follow those steps that I'm about to do. So we'll try that. We'll do remove -r processor, any processor folder, and then we just want the 0 folder. Remove all that, and then they said force decompose. So decompose -force. This is going to take a little bit longer than the first time, but still not that long. And then we try again. And now it will work. This potential foam shouldn't take too long. It only does it for one time step. So, yeah, that was quick. And then we simply just do simple SIMPLEFOAM. You can't use autocomplete for this part. It's kind of stupid, but hopefully it works now. So we will run it. And this will take some time. So we know that, I think we said there's 0.3 seconds, so this is at 1% now. And you can see my computer is chugging along. But yeah, now it's at 2%. So right now it's 8:45. So I will come back in a few minutes when it's done. Probably no more than 10 minutes, I think. But okay, I will see you guys there. So it's now 8:55. So that was about 10 minutes. So 10 minutes for decomposition, 10 minutes for running, but I'll show you in a second. I don't think that the full 10 minutes for running is necessary. We'll first look at our results with paraFOAM again. Oh, sorry, we actually need to reconstruct first. This might take a few seconds. Oh wow, not really at all. paraFOAM to see our results. And a quick apply. And you can see it load into memory. You see my RAM go up. This should ideally be less than 50% right now, which it is. Which is good. So you see here that there's 3 time steps. 0.1, 0.2, 0.3. That's because we did all the way till then. But okay. And then we'll just recreate what I did to start out with. So we'll do the stream tracers. So this is the stream tracer button, and then you pull up all these options for stream tracers. Ooh, that was glitchy. And then we want to, what it's saying is that it'll do it on a line. So we need to come up with some good points. We'll just do it at the front of the domain. So -1.3, -1.3. So then it'll be right on this front. However, I mean, we could do it on this diagonal line, but let's just first better do it on a flat line. And then across the width of the domain. And then right now we'll start with 1,000. That's typically overkill, so we'll just do 200. This is the amount of points it will make. And there we can see, yeah, some pretty cool stuff. So, but you can't see the wing. It's kind of annoying. So what we'll do is we'll do File, Open, and we'll open it again. Now, be wary that this will now open up like the same amount of RAM, which is why I said you need to have at least 50% for free, because you're basically going to double it. But that's fine. We have the space. If you only have 8 gigs, you might struggle here. What you could do is you could open up the OBJ file, which is way less. So then you'll have your full box domain again, but what we want to do is we want to just look at the motorbike. So apply, apply. And here we can see the wing. And here is a extremely beautiful result in my opinion. So I first center it on the front axis, and then I rotate it with this, and this is beautiful in my opinion. This is an older front wing, so it was still with the Y250 vortex, and you can see that really strongly here with this. We can also put on the stream tracers the velocity, so U, and then here you can see the spinning, so it's definitely a lot higher there. We can also go to the next, let's actually first do here. We can see the pressure on the wing. There's two pressures, make sure you do the one with the dot. 0 is the pressure that was inwards, and then, or coming in, and then negative would be blue, and then that's like pulling down. So here you can see all this blue that's pulling down the wing. Amazing. And all this red pressure pushing the wing down, so this is how you have force. Up to 250 pascals, just quite a number. What we should also do is we should also test further. So let's go to the next time step. It'll take a second to load, but it should be the same or similar, and indeed it is. And they're the same on each time step. So in reality, we actually didn't need to simulate all to 0.03. We could just simulate to 0.01, and it's the same as 0.03. It reaches steady state in that speed. You know, they're all the same. So this is great. Yeah, so this is the basics of the results. I'll probably post in the next video a few more results. But if you already want a little something to look at, you can look at these stream tracers as I mentioned. And then one other thing that's really fun to look at is these slices. I love looking at these slices. So if I have enough RAM, I will, what I'll do is, I do have enough RAM to load it again if I wanted. File, open, load it for a third time, apply, and what I want to do now is I'm going to be selecting just a slice, and there we should be able to see some really cool stuff. So I will do slice, and I'll just do the default so you can see what I'm going to get at. So here we can see it's taking a slice of the domain. So what I will do is I will, let's say, put this on velocity. Actually, let's do velocity, magnitude. Ooh, I have a good idea. Let's do some glyphs. So glyphs are like little pointers. We will ask this glyph to be the velocity, and it will be scaled by magnitude. Okay, thank you for making it extremely too large. Yeah, and I should hide the slice. Maybe even hide the stream tracer also. And here you can see on a 1D slice the direction everything is going in. So you can really see now the vortices being generated here, as well as everything here. And then you can move this slice, and it will move the glyphs. Yeah, and we can move it back. Click apply, and we get some new glyphs. And here you can see some more vortices. Yeah, so this is another thing you can do. We could also turn off the glyphs, just look at the slice, and here you see the velocity or the pressure. So yeah, super cool. Maybe it would be cool to look at the velocity and only the magnitude in the z direction. So here you can really see negative z going left and positive z going right. So here you see a circle. And they're going different ways, obviously. Yeah, so you can play around with this and whatever you want. I'll probably go through a bit more of it in depth, but in principle now you have every tool you need. So super cool in my opinion. If you want to save 5-10 minutes, as I mentioned, you can go to your system folder and then look into your controlDict, and just instead of n times 0.03, let's 0.1. And we just saw that it was at steady state already at 0.1. So yep, that's all for this video. I hope you guys enjoyed and learned a few things. I really hope to also see what you guys make, whether someone maybe simulates the turning vanes or something would be super cool. Yep, thank you, and maybe see you in the next part where I will talk about seeing some better results. But for now, I hope that you have a working simulation. Thank you, and bye-bye.